All right, good morning again. Today we will be talking about the coaxial cable, and as far as this lecture, we're going to probably stop at the coaxial cable, and the next class we're going to continue with multiplexing and broadband and baseband. But we need to make sure that we're on the same page when it comes to understanding the electric kitty that goes with the whole thing. Electricity, that's what I meant. All right, so all right, oh, Control L, that's the one here. All right, so coaxial cable, actually the name coaxial stands for the signal conductor, or the signal, the center core, which is right there, and the ground reference and the shielding that is associated with that. So here's the center core, and there's a shield that surrounds the center core, and they are both separated by something that's called dielectric, which is just another name for insulator. Right? Sometimes it's some sort of a PVC material, and when there are some bigger cables, like huge ones, I don't know, maybe 3-4 inches in diameter, I never measured that, then the center core and the outer conductor, which also acts as a shield from the outside interference and from the signal escaping outwards. Sometimes the shielding happens better than others, although that's the idea. Right? Now, the outer shield and the center conductor, they share the same axes, because there's the center core is in the center, and it is, well, surrounded by the other conductor, the ground reference, and the shield that acts as, well, they act accordingly as shield and the ground reference. They share the same axes, so therefore is there's the name of the cable, coaxial cable, because they share the same axis. And sometimes you're going to hear the name concentric cable. Right? All right, let's take a look at quick anatomy of things. Well, here is a graphic representation of what it should be. Over here we have a picture of one of the cables, which looks a little bit different. Yes, it does look a little bit different because there's more than one coaxial cable that was designed and produced. And here is just this picture. Here represents if you're looking straight into it. So here's the center core. Here's the dielectric that separates the center core and, the metallic shield or ground reference. And of course, it's dressed up in a plastic jacket or some sort of a PVC jacket. Okay. Now, over here, what you can see is the shield is braided. There's a braided shield, and there's, as an extra protection. So some of the cables are double shielded to give some extra protection. You're trying to make sure that the signal doesn't escape from the cable, affecting other things and signal being lost. And it also prevents interference from outside going into the cable. So it's like a double action, right? So what do we have here? What is a coaxial cable? It's a two-conductor cylindrical, and here's the thing, transmission line. Here's the important thing. Typically comprised center conductor, an insulating dielectric material, and the outer conductor shielding. Right? Now, it is a transmission line. Why are we calling it a transmission line? Well, a transmission line is something that carries some sort of a signal. Transmission link, signal link. The coaxial cable was developed sometime around the Second World War. And the purpose of that was to provide another thing I'm going to use, a radio wave guide between the transmitter and receiver and an antenna, and mostly it was produced with the radar in mind. Radar was the new thing during Second World War. All right, so that's how some of the enemy planes and other things were being detected, and it was a new thing. That's what gave some sides the edge of things, and it was picked up by pretty much everybody. Now radar is it's a normal thing, right? But it was a new thing, so it was developed to be used as a transmission line. What else can we use to transmit signal? Well, we can use air. So if you're driving your car and you're listening to the radio, you are receiving radio waves that are being all present in the air. The air is being used as, the airspace is being used as a transmission link, right? Can't say it as radio guide because those waves propagate in all directions through the air. How does the radio receiver know which radio station to listen to, if you will? Well, it has something that's called a tuner, and the tuner will pick up the whatever carrier signal that is being produced by whatever the radio station's transmitter, and it is going to listen to only that. How can we compare this thing to something that we can relate to? Well, if I'm standing in the classroom and everybody is talking at the same time, so it's just before the class, things are nice and relaxed, everybody still keeps talking, so there's that general chatter that's going on. But if I want to talk while this whole thing is happening, if I want to talk to one particular person, we can still have the conversation, and with our brains, we can tune out everything else, all the noise, and we can just hear each other while we're talking to each other. So it's just pretty much almost the same as the tuner works in a radio, that it tunes out everything that's present in the air, because we are being surrounded with electromagnetic waves, and just tune in to that particular station that you want to listen to. Right now, you can transmit the signal through the air, or you can transmit the signal through something that's called a radio guide, which in this case is the coaxial cable. There are many uses still that are being implemented for the coaxial cable. The most popular one now that you can actually see is the internet that is provided by the cable. And the thickness of the cable that you can see if you have a cable provided internet to your home or office, the thickness of that cable is usually, well, almost 99.999%, if not 100%, it is something that's called the RG6. RG stands for radio guide, right? So, and the number 6 is just a designation. When the engineers were developing different types of cables, some of them were thicker, some of them were thinner, some would have certain thickness of the core, and some of them would have one or maybe two or maybe more shields. So different types of cables were developed to be used as the concentric cable or the coaxial cable. And those cables had to be cataloged somehow. So they were all being called RGs. RG stands for radio guide again. And in order to catalog those things, they would just go, oh, well, what number can we assign it to? Is number 6 available? Is it taken? Nope. Okay, let's call it RG6. And then some other cable that was developed is 11 available? Yep, 11 is free. So yeah, we can call it 11. So don't try to make anything out of those numbers that are beside the RGs, because they are just for the cataloging purposes. Okay. Now, of course, they have different specifications, but they are not related to the number in a technical way, so to speak. All right. Now, what do I have here? A series of standard types of coaxial cable were specified for military uses in the form of RG, and then there's a number, see, or RG number, and there's that little U. The U stands for UV rated. You see that on the cable specifications. That means that the cable can be installed outside and exposed to the elements, cold, hot, but especially the UV rays that are being produced by the sun. And the cable is not going to get damaged by the UV rays. If you install a cable that is not UV rated, if you install it outside and leave that thing to be exposed to the sun, within a year or so, that thing is just going to, you can grab it by your hand, squeeze it, and the whole thing is going to, the whole jacket thing is going to turn into dust. Right? That's how strong the sun rays are. All right. The cables date from World War II and were listed in blah blah blah. Here is the specification list published in 1962. These designations are pretty much for the most part, they're obsolete. But if you're curious, you can Google that, and you can download the whole document, right, which used to be secret a long time ago, right? Long enough. And of course, the RG designation stands for Radio Guide, and there's some references if you wish to check them out. All right, the most popular cables that you're going to encounter are the 3 kinds, plus there's one more. Right? Now, so here's the, these are not to scale, but you can have some sort of reference if you see the cable that provides internet to your home. That's the thickness. It's about the thickness of a regular type of a pen or pencil, or maybe a little bit, tiny bit thicker. Okay, so that's the RG6 size. Right now, RG59 is slightly thinner in size, and RG11 is significantly thicker in size. What does that accomplish? Well, some of the cables can carry a signal to further distance than others. And there's something that's called a characteristic impedance, which we will talk about today. I just want you to understand what a characteristic impedance is. And before we do that, we're going to have to review what impedance is, and then we can look at the differences between the impedance and something that's called a characteristic impedance. There's one more cable that I didn't put on here, is the RG58 as opposed to 59, and it does have a different characteristic impedance than these three. These three, their characteristic impedance, I can just tell you the secret. I can let you in on a secret. All 3 of them, the characteristic impedance is 75 ohms, and RG58, not 59, there's another one, its characteristic impedance is 50 ohms, right? And then so depending on what you need and what the use is and what the equipment is specified for, you should apply the proper cable. And also depending on how far you want to carry the signal and what specification, and we'll talk about that further on. Right? All right, so let's get some of the background. We're going to talk about the characteristic impedance of a coaxial cable. But in order to do that, in order for us to know what characteristic impedance is, we need to establish what impedance is, period. You might have experienced this type of knowledge intake from other subjects, or maybe you haven't. Maybe you're going to hear something like that in the other subjects again. Yes, it's all connected, and sometimes you're going to hear things that are being repeated as far as the content, and that's okay. The more the more exposure you get, the more understanding you're going to encounter. Get from the whole thing, and there's no such thing as too much information when it comes to this. All right, so as a background for impedance, right, resistor, we're going to take a look at three components: resistor, capacitor, or inductor, or coil. And in the earlier days, an inductor or a coil, you might heard that word is called solenoid. Okay, solenoid, it sounds kind of wow, very technical and mysterious. It's a coil. It's basically a coil, right? It's an inductor. All right, so let's take a look at the resistor. A resistor is a non-reactive component because its resistance value remains unchanged if the applied frequency increases or decreases. Let's just take a quick look at my board here, made out of Photoshop. All right. Zoom in a little bit. All right, so let's draw a simple resistor. All right. Here is a resistor. Okay, and it is connected, well, maybe through a switch to some sort of a power supply. Okay, we're just going to make that as a power supply here, and then let's complete the circuit so the electricity has somewhere to flow. Now, if the power supply is, well, we're just gonna call it V. If the voltage is DC, right, which is going to present a constant plus and minus, the resistor R, well, let's just, for the sake of argument, let's give it some sort of value, pull it out of the air, right? Let's give it 100 ohms. Yeah, here's a little thing, here's a little thing, and here's that thing. That's the omega, right? And it's always a good idea to put the units in brackets to make things clear. All right. It will help you with some complicated, more complex equations. All right, so the resistor's value is 100 ohms, and we have a DC. Well, the resistance of that resistor is 100 ohms. That's a simple thing. You close the switch, and the current flows, and the resistance is going to provide you with a resistance of 100 ohms. Now, let's take it a little bit. Oh, that eraser is huge. Make it a bit smaller. All right, let's make this thing an AC, which basically provides that kind of a signal. For example, sine wave. Right? Well, if let's say you have 60 hertz. By the way, as far as naming things, naming the units, I'm going to digress just a slight bit because I hear it all the time. 60 hertz, 50 hertz, 20 hertz, 5 hertz, 1, and I hear some people say hertz. No, there's no how many hertz. Hertz is the last name of a person who introduced the whole world to the frequency idea. Right? So 1 hertz. Okay, there you go. Now, if you apply 60 hertz to the circuit, the resistor is going to give you a resistance of 100 ohms. All right. How about if you give it a 600 hertz? Well, the resistor is still going to present you with 100 ohms. The resistance is not going to change. All right, let's change things a little bit. My eraser. No, that's not the eraser. There you go. Instead of a resistor, we're going to apply something that's called a capacitor. And capacitor used to also be called a condenser. So if you hear something that's called condenser, it is a capacitor. And it looks somewhat like that. Capacitor can store charges. Now, if we apply a pure DC signal, there's no hertz. All right, good. So DC signal here. What's going to happen when we close the switch? When we close the switch, let's close the switch. We're going to have, well, plus, minus, for example. We're going to, if we consider conventional current flow, which means we're assuming the current flows from positive to the negative, we're going to have current I going through the circuit. How long is that current going to last? Well, if the capacitor is discharged completely, it will want to charge. It has one plate and it has another plate, and those plates are electrically separated. So this capacitor is going to start charging and is going to start filling up the plates with positive charges here, a lot of positive charges, a lot of positive charges, and a lot of negative charges are going to appear on the other side. And they will have no way to flow because here is, well, separation. Here's the open kind of a, the circuit is open, right? So the electrons will not have a way to flow, and the charges, well, will also not have a way to flow. So to a DC circuit, a capacitor with the designation of C, here's a capacitor. Capacitor acts as an open circuit. But what is actually really going to happen? First, you're going to have an inrush of current in order to charge the plates. And once those plates charge, the current is going to stop flowing. How long does it happen? How long does it take? Well, you're talking milliseconds. Sometimes you're going to talk about microseconds. So you're going to have just a quick pulse of a current going. But if we just zoom in the time, right, what's happening? The current, while the capacitor is fully discharged and is going to start charging, you're going to have a maximum current flow. That capacitor is going to act as if it were a short circuit. It's just if you replace it with a wire. And then as the plates are going to charge, the current is going to flow slower and slower and slower, and it's going to come to a zero. It's going to stop. But if you have, at the beginning, the complete inrush, maximum inrush of the current, well, because it's going to act as a short, then the voltage between that is going to be zero. It's just like a straight wire. If you have a straight wire, and if you put a voltmeter across a straight wire, the resistance of that wire is zero, pretty much zero. Well, you're going to have the voltage equal to 0 volts. So in the capacitor, first we get the current, and then the current slows down and stops. But once it does, it's going to act as an open circuit, just like that. And if you have that pretty much joined as a wire, then you're going to have the voltage, whatever this one is, appearing on this voltmeter, right here. If you put a voltmeter here, it's going to act as so. In a capacitor, we first have the current flow, and then the voltage is going to appear. So you can say that in a capacitor, current leads the voltage. Just remember, first we get the current, then we get the voltage appearing across the capacitor. All right. Now, let's just replace the capacitor with a coil or inductor. And it's going to look like this. So many wounds or whatever, okay? And the coil we're going to designate with the letter L. Why? Because that's the way it is. Inductor, L. Excuse me. All right, what's going to happen when we close the switch? To a pure DC, coil is going to act as a short circuit. So you might as well put a straight wire there, and it's not going to make a difference. To a pure DC, that's it. But let's analyze quickly what is going to happen just at the moment when we close the switch. So before we close the switch is open, right? So nothing is happening. Coil just sits there and just being comfortable and just, just being there. Now, just remember that the coils hate change. They don't like change. So when you close the switch, you're going to give it a change of a situation, right? Boom. The circuit is closed. And the coil says, oh, I see change. I don't like it. I don't like it. I don't like it, right? So it's going to give you a maximum resistance that it can give at the moment of change. Well, the maximum resistance is going to be the maximum resistance, so ideally it would be infinite. So it's just like a circuit is open. So if the circuit is open, the voltage across the coil is going to be the maximum voltage you can get, which is going to be equal, in this circuit, is going to be equal to the voltage that's being supplied, because there's no any other components. But then what coil is going to say, okay, you give me that change, but well, you know what, I'm not gonna deal with you. If you just after you made that change, if you stay that way, I will accept the situation, but please don't change. So unless, because if you do, I'm going to resist again. So the coil is going to start letting the current pass. And as the current passes, the coil is going to become a complete short circuit, which means it's going to pass the maximum amount of current. So then you're going to have a current flow. So in the coil, first you get the voltage across each terminals, and then you get the current flow. So you can say that in a coil, voltage leads current. Okay? Now, what happens if we substitute the DC power supply with an AC power supply? Remember, coils do not like change. What's the frequency? Frequency is, well, things are changing all the time. Right? So if it's a DC, no change, plus, minus, that's it. Coil acts as a short circuit, just passes everything through. Now, let's go and make this thing AC, alternating current. All right, that's a constant change. Now, if you give the coil 20 hertz. All right. Then the coil says, "Oh, I can see some change here. I don't think I like it. I'm going to give you some sort of resistance. I'm going to resist it somewhat." All right. Well, let's say you give it 200 hertz. Oh, and the coil is going to say, "Oh, that's even more more changes happening per second. This is too much. That's even more. So you know what? I'm going to resist you more." All right. If you give it 2,000 hertz, that's a lot. For example, comparing to 20 hertz, then the coil really is going to give you resistance. So, what can we say? As opposed to a pure resistor, which its resistance will not change depending on the frequency that you apply through the circuit, the coil is not going to act like that. The coil is going to give you more resistance or less resistance depending on the frequency that you apply. The more frequency, the greater the frequency, the more resistance it's going to give you. So the resistance, you can say, is reactive accordingly, and it depends on the frequency that you apply. So we can say that the coil has a reactive resistance, and we say that coil has something that's called a reactance. And reactance, let's just see here. Resistance is represented with the letter R. Reactance is represented with the letter X. Excuse me. Now, because this is an L, which represents a coil, we're going to make it XL, which represents inductive reactance. What's reactance? It's a reactive resistance. Why is it called reactive resistance? Because the resistance changes depending on the frequency that you apply. So the coil, the more frequency you apply, the greater the frequency is, the more the coil is going to resist. Capacitor, on the other hand, is just the opposite. Capacitor loves change. To a pure DC, capacitor acts like an open circuit. Coil acts as a short circuit. Now, let's just quickly substitute the all right. Give us a capacitor here instead of a coil. Yeah, and here. Capacitor with the letter C. All right. So the switch is closed. We have an AC source going on. And let's see, well, AC with a 0 hertz. There's no change. Capacitor hates no change. Capacitor loves change. So, but there's 0 hertz. Well, I'm not conducting. Nope, I'm not talking to you, capacitor says. All right, well, let's give it a 20 hertz. Oh, capacitor is going to say, oh, there's a bit of a change. Yeah, okay, I like it. So I'm going to conduct a little bit, just to encourage you to give me more. All right, so the resistance of the capacitor is going to go down a little bit. Resistance goes down. The current is going to have a little bit more comfort to flow because capacitor is not going to resist as much. All right, let's go 200 hertz. And capacitor is going to say, oh, yeah, give me more change. I'm going to resist less and I'm going to conduct more. And so on. If you give it 2000 hertz, then the capacitor is just going to be just like a fish in the water and go, oh, I love you. I'm going to conduct this. I'm not going to resist. That's it. Keep those hertz coming. I'm just going to conduct the current. So capacitor also has a reactive resistance, and it has, which we're going to say, it has reactance. Reactance is a reactive resistance. And because it's a capacitor, we're going to call it XC, which stands for the capacitive reactance. All right? Okay. let's just, all right. So this is basically what I just said. In that, I explained this thing right up to here because of resistance of a nonlinear. Like I keep calling it linear or nonlinear. Technically, I can say things are linear or nonlinear, but that's as close as I can find as a description. Because I sort of call it nonlinear, but it's a little bit, well, technically sort of correct. Right? And I'll explain that to you later. So because I don't want to spend too much time on this thing. So capacitor and coils will have reactive resistance. We call it reactance. Capacitors will have capacitive reactance, XC. Inductors will have inductive reactance, XL. And here's the formula. Capacitor, capacitance, capacitive reactance. It's 1 over 2 pi FC. 2, well, is 2. Pi, well, you know what pi is. Right? And here is F stands for frequency, and the C stands for capacitance. So look, capacitance, capacitive reactance, if the frequency goes up because it's on the bottom side, then if the frequency goes up, that means this number is going to get smaller. Coils are the opposite, 2 pi FL in this case. So here's the capacitance of a capacitor, and here's the inductance of an inductor, or a coil, or a solenoid. Okay, excuse me. So if the frequency goes up, the resistance is going to go up because there is no 1 over. Right? All right, let's keep going. Now here is what's going on with the impedance. So here we have the 3 scenarios that we just talked about, and you can download this presentation soon, and you can well, read over it if you have nothing else to do. All right, now I put a little bit of a multi-sim simulation, and this is just a screenshot. You can do this if you want, and you can you're going to get these results. So I would encourage you to do that. What do we have here? We have a AC source. We have a switch. We have a resistor to provide some limitations to the current, and we have a capacitor here, and they're all in series. Now we have the resistor value of 1 kilo ohm, which is 1000 ohms. Now here, if you don't know what that is, in multisim, you can get something that's called a current probe. Okay? Oscilloscopes will display voltage. That's all they can display. But if you apply something that's called a current probe, you are going to be able to display the current, which is what we want to display. Now, this is a Tektronix scope that is present on the multisim. If you want to know how to get the current probe in multisim, just, you know what, YouTube it, all right? You're going to get like about 35-second video that shows you where to find the current probe in the oscilloscope, in the multisim, right? Now here is the specifications of what we are providing by the signal generator. I just use the signal generator here. I chose a square wave because it gives me the most sudden change. Now the next slide I'm going to go, it's going to be this here zoomed in so we can see things better. All right, there you go. See, this here is zoomed in like that. What's happening at the moment of change? This is the time that this is the supply voltage right here in the green. And over here, we have the current going through the capacitor. And over here, we have the voltage, well, across the resistor or across the capacitor, it doesn't matter. Let's say it's at the capacitor for sake of argument, right? What happens? Okay, so here's 0, and all of a sudden, boom, the voltage just shoots up high. What's happening? Remember, capacitor acts as a short circuit, so it's going to be immediate inrush of current. And as the plates charge, the current is going to go slower, 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 and it's going to go down to 0. But as the current goes down to 0, then of course the voltage is going to start appearing across the plates. And this whole thing, because it's charged, it's going to shoot down with twice much of power of the current, because it's going to, those electrons that are, or the charges that are accumulated there, they're still there. They have to go somewhere. And so not only you have this thing going down so much, but you also have that. So you're going to have like a negative inrush of current with double size, well, from here to here. So again, you got to inrush the current the other way, and the voltage is going to behave just as it is here, right? So in a capacitor, first you get the current, then you get the voltage. See that? First you get the current, time goes by, and then you get the voltage being built up. Right? Wow, cool, eh? Right. Now, here's the coil. If we have the coil in a circuit, and I'm going to click next slide to zoom in. All right, here's the zoomed in situation. So here is the power supply. No change, no change. It's just sitting at 0. Boom, it changes all of a sudden with a huge change. And the coil is going to say, no, 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 I don't like it. I don't like it. I don't like it. I'm going to resist. So I'm going to act as an open circuit. So which means I'm going to have voltage across the coil. Boom, maximum voltage. But then nothing changes. Coil says, okay, if you stay that way, I'm going to play nice with you. All right, I'll be good to you. So I'll let the current through. So slowly it's going to start conducting the current. And of course, as the current increases, the voltage decreases because the resistance decreases. So the voltage decreases, right? So the current starts flowing. So in a coil, first you get the voltage, boom, out of the coil, and then you get the current. So voltage leads current in the coil. Now here is the side-by-side, or one above the other thing, if you want to do a bit of a comparison. So in a capacitor, first we get the current, then we get the voltage. In the coil, first we get the voltage, and then we get the current. And the capacitor, current leads because it comes first. In a coil, voltage leads because voltage comes first. Right? Okay, now here is something else I want you to be aware of. What do we have in this scenario? Over here we have impedance, or you could say reactance. Doesn't matter. It's still going to hold true if you say reactance. Because what's impedance? Well, we're going to get to that very, very soon. If you choose certain values of the components, let's say this is a coil, this red line here. Well, according to what we just established, here is the frequency on the x-axis. 10 hertz, 20 hertz, the frequency goes up as we go to the right. Resistance goes up as we move up, all right? Okay, good. So now we have something here. So if you just ignore the blue line for now, as the frequency increases in the coil does not like change, and more frequency, that means more change. The coil is going to start resisting more and more and more as the frequency increases. Right? Now, capacitor, ignore the red line now, look at the blue line. When there is no frequency, the frequency is low, the capacitor resists more because capacitor, as the opposite to the coil, it loves change. And as you increase the frequency, the capacitor is going to like you more, is going to start conducting, not conducting, but it's going to start resisting less and less and less and less. Now, if you choose certain values, like for example, if you have a capacitor that has the value of 100 microfarads, and if you have a coil of the inductance value of 100 millihenries, because Henry is the unit for inductance, and if you put them together on the same graph, at some point they're going to have the same reactance, or they're going to resist with the same strength. So in this case here, if you have a capacitor of this value, this particular value, and you have a coil of this particular value, its resonant frequency, that's what we call it, is going to be 50.4 hertz. Now, if you change the values, the resonant frequency is going to be different because, well, the values are different. The reactances are going to be different here. Right? All right. So if we have resistor, and then we have all three in one circuit in series, we have a resistor, capacitor, and a coil. And if you connect an oscilloscope, you're going to see something like this. And this is the voltage. Here's the voltage across the capacitor if you have a sine wave here. And here's the voltage across the coil. Notice one thing. They are 180 degrees out of phase. If this one goes up, and this one goes up, this one is at its down peak. And if this one here goes at the negative peak, this one has its positive peak. So they are just like a mirror image of each other. Right? So this is applying sine wave to the circuit. Those voltages are going to be 180 degrees apart. What does that tell you? Well, resistance is directly proportional to voltage. If you have something that's more resistive, the bigger resistor here, if we increase the value of this resistor, more voltage is going to appear here. We're going to create more voltage drop. And if we decrease it, we're going to have less voltage drop. So keep that in mind. The reactances do have, well, they are vector values. Vector has a magnitude and it has a direction. So let's take a look at this here. Here's the 0 point as far as 0 degrees, because we have the axes, x and y axes, for example. And we have the angle. So this is 0 degrees. Resistor is a completely non-reactive component, so it is not going to have the resistance of the resistor is not going to have any angle. It's going to stay at angle 0. You see here is inductive reactance and here is capacitive reactance. And if we go back to the previous slide, they are 180 degrees out of phase. Well, they are 180 degrees out of phase. They're just opposite to each other. So, depending on the values of the components, sometimes you're going to end up with the inductive reactance that is greater in magnitude than the capacitive reactance. And sometimes it's going to be the other way. And the resistance is always going to have the angle of 0. So if we take the reactances and we sum them up, we put them against each other. In this case, sorry, I'm going to wait for someone to pick this up. Okay. All right. Sorry. Okay. So the reactances, we can just, because they are on the same axes here, we can establish the total reactance for this. Okay, now somebody's leaving a message. All right. Sorry. Okay. So the total reactance, we just sum these up. And because in this case, the inductive reactance is greater, then we're going to have a vector, the sum of that. We're going to have the vector pointing up, because you take this here, apply it to here, that's going to become that much shorter. All right, so we apply that total reactance, and you have the total resistance of the circuit. And if you draw a line draw a line from the 0 point right to this point. That's the impedance that we designated with the letter Z, or Z if you're from the States. And you see that vector also already has an angle. So in this case, the load, whatever it is to the circuit, is inductive load. It has an inductive flavor, which is the opposite of the in the other case. This load is capacitive because the capacitive reactance is greater than the inductive reactance. So the vector is going to go down this way here, and there's going to be another angle. And here's the magnitude of the impedance, and here is the angle of the impedance. How can we calculate the impedance? Well, Pythagorean theorem, okay? That's the simplest way. You can also use trigonometry if you want, right? So Z stands for impedance, resistance with the letter R, XL for the inductive reactance, XC for the capacitive reactance. All right, so cables also have, well, because they're made of physical things, cables will have conductance. What's a conductance? Conductance is the opposite to resistance. Conductance equals 1 over resistance. So cables have conductance, which is basically describes how easy the conductor can conduct electricity. They also have capacitance, and they also have inductance, because they are made out of physical things. We live in a physical world. Now, if they have conductance, that means they will have resistance. If they have capacitance, that means they will have capacitive reactance. If they have inductance, they will have inductive reactance, which means they will have impedance. Now, let me get this thing here. Okay, let's erase this complete thing here. Erase the board. Feels like the real thing, right? If we have a piece of cable, let's see if I can just draw. This is a cable. Well, that came out pretty straight lines. All right. And here is, well, here's one side of the cable. Here is the other side of the cable. Right. And here's the center core. And here's the outer shield. Okay. And here's the center core that comes out the other end. And let's just draw with the dotted line. Whoops. Yeah. Make it nice and straight, just to represent that the inner core is inside the cable. Now, if we drilled a hole in the middle of the, right in the middle, if we drilled a hole, and if we connected a wire and connected right to the inner core, and if we connected another wire to the outer shield, what do we have? We have something like a capacitor, right? With one plate and the other plate. Now, capacitance depends on how the size of the plates, how big those plates are, and the distance between them. So if we connected things like that, we could make a capacitor out of wire, out of the wire, out of the coaxial cable. And because the capacitance will increase if the cable is longer, or will decrease if the cable is shorter, because capacitance depends on the size of the plates, then if we want to measure the impedance of this cable, of the whole length of the cable, yes, it's going to change if you have a longer cable or a shorter cable. But this is not how we use cable, do we? We use cable in a little bit different way. Let's just get rid of that, and let's get rid of that. And let's fix our cable. Right. What do? We have an amplifier, radio frequency amplifier, and amplifiers are usually produced that way here. We're going to insert a wave into the cable. How is it that the wave travels? If you have a water, like a lake or a pond, if you drop a stone, the stone is going to hit the surface of the water and it's going to create ripples in the water. Now, the stone hits the surface of the water, goes down to the bottom, so then once the stone hits the surface of the water, and it just passes through, it just goes down, sits on the bottom, the waves still continue, right? They don't stop. Well, same thing with the wire, with this coaxial cable. The amplifier introduces a wave and just shoots it down right here, and the wave travels on its own. And it just gets smaller and smaller and smaller as the cable gets longer. So that's how we can say, how far the certain cable can carry the wave, right? So obviously, thicker cables with thicker gauge wiring can carry the signal further because they'll have less physical resistance. But what we're interested in is the interface between the output of the amplifier and the beginning of the cable. The amplifier only cares and is only able to see how easy or how difficult it is to insert the wave into the cable. Which means there's absolutely no difference to the amplifier as it works, whether the cable is very long or the cable is very short. It only cares about this spot right here. Now, there are different ways we can establish the formulas, and we're not going to get into that. So what I'm going to tell you is, on average, pretty much, technical term, right? The characteristic impedance is going to be equal to the impedance of the cable at the length of 1 meter. That's on average. Right. That's the characteristic impedance of the cable. That's what determines how hard the amplifier has to work to insert the cable, the wave into the cable, and the wave continues on its own. And if it inserts many waves, those many waves, they travel through the cable, but they travel on their own. So characteristic impedance is the impedance of the cable if the cable had just the first meter of the cable. That's what the amplifier cares. So in this case, is the characteristic impedance going to change if the total length of the cable changes? Well, no, because it only cares about the first meter. Now, there are two impedances that we use in the industry. One is 75, and the impedance is measured in ohms, same as resistance. All right, so one is 75 ohms, the other one is 50 ohms. All right. Okay, so now you know the difference between impedance and characteristic impedance. Now, when you order a cable at some distributor or wherever you buy the cable, sometimes or quite often, or maybe all the time, you're going to hear, what impedance do you want? They mean the characteristic impedance. They mean the characteristic impedance even if they don't know what characteristic impedance is. They mean it even if they don't know what they mean. Right? So that's what it means, characteristic impedance. Why do we need to know the characteristic impedance? And I'm going to leave you with that question, as I left the other guys from yesterday in-person class. Why do we need to match the impedance? So the impedance of the output impedance of whatever sends the signal has to be equal to the input impedance of wherever the signal is going in. Why is it important? So if you have a cable that is specified for 75 ohms characteristic impedance, you better have an amplifier that has an output impedance of 75 ohms. Okay, I almost answered the question for you. Right? If you have an amplifier that has 50 ohm impedance on its output, you better get a cable, coaxial cable, that has a characteristic impedance of 50 ohms. We need to match those impedances, and I'm going to leave you with an open question, and next time we see each other, maybe we can talk about why is it important that the impedances are matched. All right, so now you know what the difference is between the impedance and the characteristic impedance. So go and impress the world with your knowledge. All right. Well, we went over time a little bit. I hope you didn't mind, but now you know what you know. And I will see you when I see you. Some of us, I'm going to see you tonight. Thank you very much. Have a good one.